All right, so next up we're going to talk about steps to solve line integrals for vector valued functions f. And we're actually going to break this up into two different cases. So if f is conservative is the first case. Then you can find the potential function f so that your vector valued function f is the gradient of that scalar function. And you just have to identify the endpoints of C, so that C is something that goes from, I think I said Q and ends at P. Just like in that picture over there. Starts at Q, ends at P. And then from there you can just calculate that the line integral of f is going to, capital F, the vector, is going to be little f, the scalar function, evaluated at the endpoint, and then subtract little f evaluated at the starting point. And most importantly, what this means is that if your curve C ends and starts in the same place, you're always going to get 0. So if f is conservative and your curve is closed, go ahead and skip everything and just say the integral is 0. Again, that's only for f conservative and C closed. And by closed, I mean it doesn't really matter what happens in between, but you start and end in the same place. That's a closed curve. The more complicated case is going to be if f is not conservative. But our good tool parameterization is going to be how we solve this type of problem again. And it's going to be pretty much exactly the same as how we solved line integrals using parameterization for scalar valued functions little f. So we're going to start out by identifying a parameterization, but this time we want it to be a vector parameterization. And so what that's going to be is some curve that's vector valued r equal to x of t I hat plus y of t j hat plus z of t k hat with bounds for t a less than or equal to t less than or equal to b. That's the other representation we came up with for parameterized curves way back when we learned that material. And then you're going to plug in x of t, y of t, and z of t to your vector valued function f that used to depend on x, y, and z to get f a function of only t along your parameterized curve. And you're going to calculate that dr is your vector parameterization r's derivative, r prime of t dt. And you're going to use bounds of integration a to b from your bounds for t, a less than or equal to t less than or equal to b in the parameterization. And then we're going to check that only t is left in the integral. I know it's silly that I write this as a step, but it's important. And what it should look like now is that you used to have integral over c f of x, y, z dotted with dr. And it should look like an integral between two numbers of f that depends only on t, dotted with r prime, also a function of t. And you're going to, okay, cool, evaluate this whole integral with respect to t. And then from there, you just have to compute this dot product and evaluate the integral, which again will just be a simple calculus problem, because it'll be that the dot product, turn this into a scalar function of only t, you have an integral with respect to t that's bounded.